Voyager 2 accomplished something Voyager 1 never could, and what it found has just been confirmed. Two machines, same mission, same launch year, but only one of them was carrying an instrument the other lost decades ago. And when it crossed into the dark beyond our solar system, it measured something no human instrument had ever measured directly before. The results contradicted everything scientists expected. And right now, NASA is running out of time to keep it alive. Welcome, my friends, to Universe Secrets Revealed. If you are someone who still believes in taking a moment to sit down, listen carefully, and actually understand the world above us, rather than simply scrolling past it, then you are exactly the kind of person this channel was built for. So I ask you respectfully, as you would do for an old friend, sharing something worth knowing, press that subscribe button and stay with us. And before we go further, tell us in the comments from which city, which country are you watching this from today? We would love to know who is with us on this journey across the stars. Now, let us begin. Right now, at this very moment, two machines are traveling through interstellar space. Most people know about only one of them. That spacecraft crossed beyond the edge of the solar system in 2012, carries a golden record, and continues to make headlines even today. But there is a second spacecraft out there. It moves through the darkness in a completely different direction, sampling a completely different part of space, and yet almost nobody talks about it. Its name is Voyager 2. It launched on August 20th, 1977, just 16 days before its more famous twin. This small difference in timing might seem unimportant, but it hides a much bigger story. Despite launching first, Voyager 2 was given a longer and far more difficult journey. While the other spacecraft was sent on a fast, direct path toward the edge of the solar system, Voyager 2 was sent on a route that would let it do something no other spacecraft had ever done before, and something that, almost 50 years later, still no other spacecraft has repeated. Voyager 2 became the only spacecraft in human history to visit all four outer planets: Jupiter, Saturn, Uranus, Neptune. Every single gas and ice giant in the solar system, seen up close, studied in detail, one after another. Its twin, meanwhile, took a shorter path. It visited only Jupiter and Saturn before turning away, sacrificing the chance to ever reach Uranus or Neptune in exchange for a faster route out of the solar system. Two spacecraft, two missions. Two very different journeys built from the very beginning to answer the same question in two different ways. What does the true edge of our solar system actually look like? But the price Voyager 2 paid for its longer journey was time. Because it took the slower path, it did not reach the true boundary of interstellar space until years after its twin had already crossed it. For 6 long years, scientists only had data from one direction, one spacecraft, one point of view. And that data, while extraordinary, told an incomplete story. Because hidden in this story is a fact that almost nobody mentions. One of the two spacecraft was carrying a critical scientific instrument that had already stopped working, decades before it even reached the boundary it was sent to study. It had failed silently, years earlier, long before anyone even knew it would matter. The other spacecraft was still carrying that same instrument, fully working. And when it finally reached the edge, that single working instrument would end up changing everything scientists thought they understood about where our solar system ends and where the rest of the galaxy begins. That spacecraft was Voyager 2, and what it was about to find would not simply confirm what had already been discovered, it would contradict it. The spacecraft that everyone recognized crossed into interstellar space first, in August of 2012. But it did so carrying a serious limitation, one that had existed for more than 3 decades without most people ever knowing about it. Its plasma science instrument, the device built specifically to measure the temperature, density, and movement of charged particles both inside and outside the solar system, had stopped working back in 1980. This was not a failure that happened at the boundary of interstellar space. It happened years earlier, before the spacecraft had even passed Jupiter on its outward journey. By the time it finally reached the true edge of the solar system, more than 30 years later, the one instrument best suited to explain what that edge actually looked like had already been silent for decades. Scientists still learned a great deal from that first crossing. They used other instruments, cosmic ray detectors, magnetometers, plasma wave sensors, to piece together an indirect picture of what was happening. But it was exactly that. A picture built around a gap, not a complete and direct measurement. Then came the second spacecraft. Voyager 2 crossed into interstellar space 6 years later, on November 5th, 2018. And unlike its twin, it was still carrying a fully working plasma science instrument, one that had somehow survived more than 4 decades in the harsh radiation environment of deep space. For the very first time in the history of space exploration, scientists had a spacecraft crossing this boundary while still able to directly measure the plasma on both sides of it, inside the solar system and outside it, at the exact same moment. The results were described by researchers as historic. In November of 2019, 5 separate scientific papers were published together in the journal Nature Astronomy, describing everything Voyager 2's instruments had found at the boundary. And what they found did not simply support what scientists had already believed. In several important ways, it directly contradicted it. This was the moment the story shifted. For 6 years, the world had built its understanding of the edge of the solar system using only partial information, gathered by a spacecraft that could not fully see what it was passing through. Now, for the first time, there was a complete measurement. And that measurement revealed that reality at the boundary was more complicated, more surprising, and in some ways very different from what every existing model had predicted. What makes this even more remarkable is that none of it happened by accident. Decades earlier, in the 1970s, the engineers who designed the Voyager missions built 2 spacecraft on purpose, knowing that a single spacecraft could never tell the full story on its own. One data point could never reveal whether what it found was typical or unusual. 2 spacecraft, approaching from different directions at different times, could begin to build something no single mission ever could. A real comparison, a way to check one discovery against another. What they could not have fully predicted was that one of those 2 instruments would fail so early, and that the other one would still be working 4 decades later in exactly the moment it was needed most. That is the quiet story behind Voyager 2. Not simply a spacecraft that visited more planets, a spacecraft that, through nothing but the survival of one working instrument, ended up filling a scientific gap that had existed since 1980 and gave humanity its first true, direct look at the true edge of the solar system. And the surprises found in that data were only just beginning. When scientists finally opened the data from Voyager 2's crossing, they expected confirmation. What they found instead was closer to contradiction, and it arrived in 3 separate surprises, each one challenging an assumption that had stood for decades. The first surprise involved the shape of the boundary itself. Before this crossing, scientists believed the edge of the solar system would look like a thin, sharp line, a narrow zone only a few 100,000 kilometers wide, where the hot solar wind pushing outward from the sun would meet the cold plasma of interstellar space and quickly separate. Instead, Voyager 2 found something else entirely. It detected a wide transition zone, roughly 100 million miles across, sitting just outside the true boundary. Interstellar material was pushing inward through this zone, like roots slowly working their way through rock, mixing with the outward-flowing solar environment in a way no existing model had predicted. The edge of the solar system was not a line, it was a layer. There was something even stranger buried inside this discovery. Both spacecraft crossed the boundary at almost exactly the same distance from the sun, even though one crossing happened during a period of high solar activity, and the other happened during a period of low solar activity. Scientists had long believed the size of this boundary should expand and shrink depending on how active the sun was at the time. Instead, it barely changed at all. One of the senior scientists working on the mission stated plainly that they did not understand why. That kind of admission, coming from someone who had studied this data for decades, was itself remarkable. The second surprise involved temperature and density. The solar wind carries plasma outward from the sun at extremely high speed, which in physics terms means it is very hot. Scientists expected that as this hot plasma reached the boundary and met the colder, denser plasma of interstellar space, the change in temperature would happen gradually. What Voyager 2 actually measured was a much sharper drop than predicted, a fast transition from one extreme to another. At the same time, the spacecraft confirmed something equally important. Interstellar space was not empty. The plasma beyond the boundary turned out to be more than 40 times denser than the solar wind found at the edge, and its temperature, measured directly for the first time in history, came out significantly different from what earlier estimates had suggested. The old estimate had been off by roughly a factor of 2. The third surprise, described by one of the mission's lead scientists as the most remarkable of all, involved the boundary's behavior. It was not a solid wall, it leaked literally in both directions. As the first spacecraft approached the boundary years earlier, it detected small amounts of interstellar material pushing inward into the solar system. When Voyager 2 approached from a completely different direction 6 years later, it detected the opposite happening, a slow trickle of particles from inside the solar system leaking outward into interstellar space, even before the spacecraft had fully crossed the boundary itself. 2 spacecraft, approaching from different angles years apart, both discovered the same underlying truth. Material was crossing this boundary constantly, in both directions, through mechanisms nobody had fully explained before. One senior scientist offered a description of this discovery that captured its significance clearly. He said the Voyager spacecraft were not showing where the solar system ends and interstellar space begins. They were showing how the two interact, continuously like a coastline rather than a wall, where the tide moves in both directions at once. Taken together, these 3 findings did more than add new numbers to old models. They reshaped the basic understanding of what the edge of the solar system actually is. Not a clean, sealed boundary separating one environment from another, but a wide, active, constantly shifting zone where 2 very different regions of space are still, even now, influencing each other. And all of this had been made possible by a single working instrument, on a spacecraft nobody had been paying close attention to, quietly measuring what no one else could. By the summer of 2026, the story of Voyager 2 had shifted from discovery to survival. Both spacecraft were now operating on borrowed time, powered by the same slow, unstoppable process. Each carried a radioisotope generator, a device that produced electricity from the natural decay of plutonium. This decay could not be paused, slowed, or reversed. Every single year without exception, each spacecraft lost about 4 watts of usable power. At launch, each one had roughly 470 watts available. Nearly 50 years later, that number had shrunk dramatically, and it kept shrinking. Voyager 2 still had a slight advantage over its twin. It carried more remaining power and still operated 3 working science instruments. The plasma science instrument, responsible for the historic helopause measurements, a functioning magnetometer, and a working plasma wave subsystem. Its twin, by comparison, had already lost one of its instruments earlier that same year in April, when falling power finally forced it offline. Voyager 2 was, for the moment, still whole. But the same mathematics that ended one instrument on one spacecraft was steadily working against the other. This is where a new, high-risk plan entered the story. Engineers at NASA's Jet Propulsion Laboratory had been developing a procedure nicknamed, informally, the Big Bang. It involved reconfiguring almost every remaining powered system on the spacecraft at the same time, shutting some systems off completely and replacing others with lower power alternatives, all in a single coordinated operation. The reasoning behind doing it all at once, rather than gradually, came down to risk. During any partial reconfiguration, a spacecraft passes through unstable in-between states, moments where the system is neither in its old configuration nor its new one. These unstable states can trigger automatic safety systems built into the spacecraft, systems designed to shut things down the instant they detect the power draw exceeding what the generator can supply. The longer a spacecraft lingers in one of these unstable states, the higher the risk that something shuts down permanently without warning and without the ability to reverse it. The Big Bang was designed to minimize exactly that risk by moving through the transition as quickly as possible instead of drawing it out. But there was a serious complication. Every single command sent to Voyager 2 took more than 16 hours to arrive. Every response took more than 16 hours to return. There was no way to react quickly if something went wrong mid-procedure. There was no backup plan, and there would be no second attempt. If the procedure succeeded, it could extend the operational life of Voyager 2's remaining instruments by at least a year, possibly more. And if it succeeded on Voyager 2 first, the same high-risk procedure would then be attempted on the other spacecraft, with engineers hoping a successful outcome might even allow its lost instrument to be brought back online. Behind all of this sat a much larger and more uncomfortable truth. There was no replacement mission waiting to take over. No other spacecraft existed anywhere near the region these two machines were currently exploring. Nothing else was positioned to continue measuring the true edge of the solar system, or the strange leaking boundary these two spacecraft had spent years mapping. The questions raised by their discoveries about the true shape of the solar system's boundary, about the unexplained consistency in where that boundary sat, regardless of solar activity, about the mechanics of a boundary that let material pass in both directions, remained open. And they would stay open for as long as human institutions took to design, fund, and eventually launch something capable of reaching that same distance again, a process that could easily take decades. Until then, everything now depended on 2 aging machines built with technology from the 1970s. Running on a fuel source that could never be replenished, still transmitting from a place no other instrument could reach. The signal from Voyager 2 was still coming. Faint, delayed by more than 16 hours, but still coming. And whether it kept coming for another year or fell permanently silent during a single unrepeatable procedure was a question that, by the summer of 2026, no one on Earth could yet answer.